Welcome to this video on fluid dynamics mathematics. We will explore the essential mathematical tools and equations used to describe and analyze the motion of liquids and gases. To begin, fluid dynamics is the branch of science that studies how fluids move and how they interact with forces. The history of fluid mechanics is rich, featuring significant contributions from great minds like Archimedes, Bernoulli, Euler, and Navier Stokes. What defines a fluid? It is a substance that continuously deforms when subjected to shear stress. Let's look at key fluid properties. First is density, which is defined as the mass contained in a unit volume. It is a critical factor influencing buoyancy, pressure, and general flow behavior. For instance, water has a density of approximately 1,000 kilograms per cubic meter. The formula for density is mass divided by volume. As shown in this example, a fluid with a mass of 50 kilograms occupying 0.05 cubic meters results in a density of 1,000 kilograms per cubic meter. Another important property is specific gravity, calculated as the ratio of the fluid's density to the density of water. This is a fundamental value used in engineering analysis and fluid system design. Pressure is defined as the force acting per unit area. It is represented by the formula P equals force divided by area and is essential for fluid system design. Hydrostatic pressure refers to the pressure exerted by a fluid at rest due to the weight of the fluid above a given point. It is calculated using the formula P equals rho g h, where rho is density, g is gravitational acceleration, and h is the depth. Fluid statics is the study of fluids at rest. This field encompasses principles like hydrostatic pressure, pressure variation with depth, and buoyancy, also known as Archimedes' principle. Conversely, fluid dynamics is the study of fluids in motion and the forces acting upon them. It covers complex phenomena such as boundary layers, lift, and drag. Flow types can be categorized in several ways, including steady or unsteady flow, as well as uniform or non-uniform flow. Streamlines are imaginary lines that are everywhere tangent to the instantaneous velocity vector of a fluid, providing a visual representation of the flow direction. A velocity field is a mathematical construct that represents the fluid's velocity at every individual point within a space. Finally, the conservation of mass is a fundamental principle in fluid dynamics, stating that mass cannot be created or destroyed within a system. Now we examine the continuity equation. Represented by the formula A1V1 equals A2V2, it is a primary tool for engineering analysis and designing efficient fluid systems. For more complex scenarios, we use the differential continuity equation. This accounts for variations in fluid density, time, and the velocity vector across the divergence operator. The Reynolds number is one of the most vital dimensionless values in fluid mechanics. It allows us to predict flow behavior and determine whether the fluid state is laminar or turbulent. The formula for the Reynolds number incorporates density, velocity, pipe diameter, and dynamic viscosity. Based on the calculated value, we classify the flow as laminar, transitional, or turbulent. Laminar flow occurs at low Reynolds numbers. In this state, the fluid moves in smooth, orderly layers without significant mixing. Transitional flow is found at medium Reynolds numbers. Here, the fluid is susceptible to small disturbances that can escalate into turbulence. Turbulent flow is characterized by high Reynolds numbers. This state involves chaotic mixing and irregular fluctuations within the fluid. The Bernoulli principle is a cornerstone of the field. It describes the conservation of energy in flowing fluids, linking pressure, velocity, and elevation. A practical application of the Bernoulli principle is the relationship between pressure and velocity. As a fluid's velocity increases, its pressure decreases. The momentum equation is the fluid equivalent of Newton's second law. It is essential for understanding how forces impact the motion of fluids. The Euler equation provides a simplified version of the momentum equation, specifically applicable to inviscid flows where viscosity is neglected. The Navier-Stokes equations are the fundamental governing equations for fluid motion, accounting for both viscosity and internal forces. The boundary layer is the thin region near a solid surface where the effects of fluid viscosity are most significant. Drag force, expressed by the formula Fd equals 1/2 rho v squared CdA, measures the resistance a body experiences when moving through a fluid. Finally, lift force is generated by pressure differences across an object, a principle critical to aerodynamics and engineering design. Moving on to dimensional analysis, this powerful technique simplifies complex physical systems by reducing the number of variables into essential dimensionless groups. This process relies on the Buckingham pi theorem, which provides a formal method to transform a set of variables into a smaller, equivalent set of pi groups. Computational fluid dynamics, or CFD, uses numerical simulation in computers to solve the complex equations governing fluid flow, allowing for detailed analysis of physical systems. These mathematical foundations are applied across many engineering fields, including aerospace, marine design, fire protection systems, and HVAC engineering. Consider the example of fire pump hydraulics. Engineers apply these principles to accurately calculate flow rates, pressure losses, and nozzle performance to ensure safety. In conclusion, fluid dynamics bridges mathematical theory and physical reality. By mastering these principles, we can predict and engineer solutions to complex challenges in the world around us.